So this tutorial is on OpenFlow, SDN, and NFV. Three clear topics, three different modules. First about the OpenFlow, then about SDN, and then about NFV, what these things are, right? In the OpenFlow part, we'll talk about planes of networking, what is OpenFlow, what switches implement it, how it is evolving, what are the other protocols that go along with the OpenFlow. In the second part, we talk about software-defined networking. Again, what is SDN, and what are the things other than OpenFlow also which can be used in SDN. So how they relate to SDN, XMPP, PCE, blah, blah, other things. And then we talk about Open Daylight SDN controller platform. Then we go into network function virtualization, NFV. NFV and SDN relationship, what is happening in HC, and what has been done so far, right? So this is all we're going to talk about in the next 3 hours. If this is not the one, you also have a choice of another tutorial, which is on open, that is called congestion control and flow control in data centers, which is in the next room. And basically, so you should know there are 2 tutorials going in parallel. Okay. With that, we begin on part 1, OpenFlow and tools. We already talked about a minute ago that we will talk about planes of networking and OpenFlow operation and evaluation. So let's go right into it. There are 4 planes of networking: data plane, control plane, management plane, and service plane. Okay. What is the data plane? So everything that the user sends, every bit that the user sends is data bit. And wherever it flows, we call it a data plane. But to send those data bits, the network has to send more than those bits. It has to add a header. It has to have routing messages. It has to have, make routing tables. All these extra messages are either control or management. So how do you distinguish control and management? Control is those messages which are really essential for the operation of the network. Without that, the network will not function, such as a routing table. If you don't have a routing table, you can't send the packets from here to there. Managements are those bits of the extra bits that are optional, that are not required for the functioning of the network, but that are required for performance, that are required for reliability, that are required for fault tolerance, and so on, right? But that is all optional. Suppose in your company, you have managers. Managers are optional. If everybody does the job, managers have nothing to do, right? They can stay home. And so management plane consists of everything that is optional. It is required for FCAPs. FCAPs is fault, configuration, accounting, performance, and security. Of course, they will be required for accounting. If you have accounting, but generally in home networks, for example, we don't need management. Everything is unmanaged and it goes fine. And so to turn on the device, to turn off the device, these things are management plane, and the control plane is everything else, which is basically essential, right? So that's like secretaries. Without secretaries, the department will not work, and those are control plane. Service planes. So now what is a service plane? Now there are many things that we did not do initially, but later on we realized that it will be good to have them. And these are kind of functions that we put in the network, such as load balancing, firewalls, proxies. Now these do not fit in the original 3-plane model, so these are called middle boxes. They're not in the end, they're not in the host anyway. So we call them middle boxes. And again, they are optional for the most networks. They're mostly required for large networks. So that is the service plane. So those are the 4 planes. Now, what data plane is, the data plane consists of user bits. We need to send it at the line rate. So if you have a 10 gigabit link, the user expects that the bits will get out at 10 gigabit. Control plane is not that fast. You can make routing table once a day, once an hour, once a minute, whenever you want to make them. So the control plane, you have some flexibility about how fast it goes. the data plane has to go at the line rate. So the data plane is generally implemented in the hardware, mostly the specialized hardware, and the control plane is generally implemented in software, mostly in a CPU or a processor that might be there, a cheap, very slow processor on the router or the switch or whatever. And so there is a data logic and the control logic, right? So it's also called a slow path. So the control plane is on the slow path. Sometimes the data traffic also goes on the slow path. For example, if you have a broadcast, unknown, or multicast, you might send it to the CPU to figure out what to do with it and then come back. So data might go into the slow path, but generally data goes to the fast path. The open flow idea that came from Stanford was that we should separate the two planes and put all the control in a central place and make the data plane flow based. So I will explain these three concepts, in more detail, but let's first go through the history, how it all happened and why it all happened. So in 2006, United States started research on next generation internet. Next generation internet research, we called it, I forgot the name even. Anyway. So clean slate research, as you know. But basically, Martin Casado, a PhD student at Stanford, came up with the idea that the security is not done correctly right now. It is done basically at the edges. So what we do is, for security, we put a firewall at the edge of the network, and once the packet come in, pass the firewall, they can go anywhere they want, which is not right, right? And so he said, why don't you put a guard at every door so that when you go to your room, you will be checked before. So not just at the edges, but at every switch. And so that's a good concept. And to put the guard at every door, basically you have a central controller which tells each guard what is the policy right now, which packets are allowed to come in which room, and all that, and so on and so forth. And that concept was called SANE, funded by NSF. The next proposal after this was called Ethane, funded by NSF. And then they said, well, why do we have to stop at security? Even forwarding can be done the same way, with the central place telling you how to forward the packets. So that became OpenFlow. The paper came out in 2008. The specs came out in 2009. Industry liked it, so they formed a foundation in 2011. Open Networking Foundation was formed. And before that, in 2009 and 10, two people from Stanford formed companies. Martin Casado formed Nicira, and Guido formed Big Switch Network, right? And in 2011, first conference happened on Open Networking Summit. And everybody announced, the whole industry announced that they want to go with this thing. And then in 2012, VMware bought Nicira for $1.26 billion. So now Martin Casado is a billionaire. And Cisco also spent about $830 million buying its own company by its own employees in Symie, somewhat related to SDN. Anyway, right now, every company in the industry is doing SDN. SDN is here. SDN is real. Okay? So, any question or comment so far? Like I said in the morning, most of you were there in the morning, I think. So, please do interrupt me. And more you interrupt, the better it will be for you and for me. All right? Because then I know that it is getting through, that what you are interested in, we discuss that rather than what I am interested in. Right? Any questions so far? We need to have one question to begin, so that icebreaker. Nobody has a question so far? Everybody is happy with this? All right, moving on. So the idea was that the switches have two parts, the control logic and the data logic. So we just leave the data logic, move the control logic to a central computer. So these are called forwarding elements. The central controller basically gives them the forwarding table So the whole routing is done in the central controller and sent to the forwarding elements, and then they can just forward the packet. When the packet comes in, they look at the header, they match the header, and they send it off. They don't do any OSPF or spanning tree or any of the things that we talked about in the morning. They just do simple table lookup and forward. And the protocol that is spoken between the controller and the forwarding element is called OpenFlow. So OpenFlow is a protocol that allows the controller to tell the switch, okay, please, change your line 7 in the routing table to this. Or for the switch to ask the controller, what do I do with this new header which is not in the table right now? So that protocol is OpenFlow. Now, second thing they said, that the controller is centralized. So that controller will decide all the path and give it to all the forwarding elements. So right away the question occurs to all of us who are trained to be thinking about distributed systems, distributed networks. Why centralize anything, right? So I'm going to give you several reasons why centralize. First of all, the whole world is centralized. When you go to your office, it is centralized. You report to your boss, they report to their boss, they report to their boss. Think what will happen if your company was distributed totally, peer-to-peer company. So you have 100 people. When you get sick, you tell all 100 people, look, I am sick. And so they will then find a way to rearrange their work so that your work is done. And then when you get okay, then you tell all 100 people that I'm okay, and they will rearrange their work so you have something to do. It will take quite some time for them to know and for you to know, right? Very inefficient, isn't it? But that's how the current network works. That's how the OSPF works. That's how the internet works, is that you tell everybody, once they learn it about the situation, then they take action, right? So it's not very fast. On the other hand, with a centralized approach, you tell your boss, look, I'm sick today, and the boss somehow arranges your work to be done. And then when you get okay, you tell the boss instantly reassigns the work to you, and you're done. So any situation like this, the recovery, etc., can be done much faster with a centralized manner than a distributed manner. Response to changes is very fast, and also management is fast. By the way, management has always been centralized. Even on day one, in the internet, control was distributed. This management was centralized, and control was very, very distributed. I will tell you what. When the initial network were telephone networks in 1968, telephone network was actually had control plane and the data plane totally confused. Confused in the sense that totally merged, and on the same wire they had analog voice going and they had control frequencies going. Those were the days when Stephen Jobs and others could send some tones to tell the switch that please send this call to this place, and they could make free calls, right, using tone generation. Well, telephone company figured out that they need to separate the control plane and the data plane, and so they put two networks, one data network for users thing, and one control network for their thing. So now you cannot do those tone generators anymore, because you cannot send a bit on the control plane. Okay, on the internet, we are still confused. Every packet has a header, which is actually control plane. And then on the top of that, there are many messages which are control messages completely, which are not sent by the user. It's very difficult to separate. Of course, we cannot separate the header, but even so the idea is now we are thinking about centralization. Any questions about that? Anybody objects to that? No one objects to centralization. Yeah, go ahead. So what is called centralization? Scalability. Good. All right. You see, I'm really surprised that nobody else asked a question, because I didn't get a call sleeping right now after lunch. But coffee is available, by the way. They said the coffee will be there ever. So if you feel sleepy, please wake up. We have been taught that centralization is bad from day one. From when you started the networking class, we have been taught. Why? Why? Because the day when the internet was designed, it was the central network was already there. There was an AT&T network. And the United States was afraid that if Russia were to bomb this AT&T headquarters, everything will go, nobody will be able to talk to anybody in the United States. So they asked for a different solution, which was designed totally differently. So everything telephone company was doing, we did just the opposite. They were centralized, we did distributed. They were circuit switching, we did packet switching. So we have been taught that the circuit switching is bad, distributed is good, and centralized is bad, and so on and so forth. So I'm surprised that nobody asked as to why centralized now. But now this is 2 generations later, 40 years later. After every generation, the thinking changes. Things are cyclic, right? So circuit switching and all of those things, are not that bad. Now distributed. Now coming back to his question, he says centralized has a scalability issue. So you can centralize, you can manage maybe 1,000 people, but can you manage 1 million people? No. But distributed also has a scalability issue. If you have 10 nodes, they can talk to each other and do peer-to-peer OSPF. But if you have 1 million nodes, they can't. You will have to tell 1 million people every time a link goes down, you have to tell 1 million people, look, the link went down, and then they will have to do the extra and whatnot, right? So what we do in OSPF is we divide the big network into areas, OSPF areas, and each area is very small because the distributed system has a scalability limit. Okay, so both have that scalability problem, distributed as well as centralized. The limits may be different depending upon what you want to do. However, in both cases, the solution is hierarchical, means make a big thing into small pieces, make those pieces into even smaller pieces until they become manageable. So in the case of centralization, what we do is we have 5 managers and they report to another senior manager, they report to another vice president. So there is a whole hierarchy of centralization. Similarly, on the distributed side, you could have OSPF and then BGP and then whatever you want, right? So we have to divide in either case into smaller areas. Now, the second issue is centralized versus distributed is reliability. Centralized, people will say, if you just kill that central place, then the whole thing will go away, right? Whereas in distributed, if you kill 999 of the 1,000 routers, the 1,000th router will still keep working and will have no problem. So the idea there is that, of course, you want to centralize, but you want to also have standby. You want to have, if the manager is not there, then there is a standby manager, there is an assistant manager, or there is somebody else, just at that level who can take care of that part. So reliability has to be fixed and can be fixed, and people are now working more research on that area, is as to how to make the centralized controllers more fault tolerant, right? So anyway, so the debate between centralized and distributed has gone on for very long, but it was very much biased towards distributed. Now it is very much biased towards centralized. Believe it or not, the industry is buying the centralized stuff. And the reason they're buying the centralized stuff is because the networks are becoming too big. Now, we talked about this morning, the data centers have millions of VMs to manage. Distributed stuff can be done, but it will have to be made very small pieces, and that will be too much. So with centralized stuff, it is possible to do that. Okay, and so all this cloud computing and data centers are asking that you want to have not too many people, just one person sitting at a terminal and somehow saying to 1,000 people, please change your table, and everybody changes the table. So that is what is happening. The number of devices is becoming so large that it is just much easier to send it from one place than to have it totally be recomputed every time there is a distributed system. Does that make you happier? Or all right. So I would not have given all these arguments 5 years ago because we didn't even think in centralized terms at all. But today the world is getting centralized. OpenFlow version 0.0. So version OpenFlow. So what OpenFlow says is that you have a table where we have the header fields, and each row has a header field. If this matches, then you implement these counters and do these actions. So what is in the header fields? Header field has ingress port. What wire did it come on? Ethernet source, Ethernet destination, VLAN ID, VLAN priority, IP source address, destination source address IP protocol type, type of service, TCP port number, layer 4. Remember this morning? Okay, so layer 4 is OSI layer 4, TCP, right, or UDP. Port number, destination port number, and source port numbers. All of these things you match. If it matches there, then you do the actions and the counters that are indicated. Here is an example of a table. The first entry says **0A: C8. If the destination MAC address starts with 0A: C8, then everything doesn't matter. Just send the packet to port 1. Okay? And increment the counter number 102. Now the counter number 102 will tell you whether it is packet counter or a byte counter. Okay? And so you can implement that. If the destination IP address is 192.168. whatever, it doesn't matter, send it to port 2. Okay? Increment the counter number 202. On the other hand, if it is an ICMP packet, drop it. Okay? If it is protocol type 806, then it is local, means send it to your own stack, switch stack. You want to talk to the switch sometimes and not just transfer the packets through it. So then it will go to the local stack and the counter number 444 will be incremented. If the protocol type starts with 1, 0, 1, the last one, then send it to the controller. Okay? So this is an example of and you see most of the entries are stars, means, wildcard, and there are some specific things that you want to match. Now this table can become very big, and therefore we have to make sure that only entries that are active are there. So every entry, every row has a timeout. If it is not used for that long, then that row is gone. Some new row will come in as required. There is a hard timeout. That means all the rows will go away after some minutes, and new entries will come in from the controller. All right. So basically now there is a routing table which looks like this, and it comes from the controller into the forwarding element. Yeah.
Before we have a higher, now we use that, and then do a large table. But then we leave all the control to the control plane. We just deal with the large table. You want that one or whatever you need to the.
Yes, you have right. Basically, what we do is we have lots of controllers. Each one is responsible for a certain area, and they give you the table, whole table, and which could be large, basically depending upon how micro you want to be, what specificity you want. Yeah.
So it's not like we peel the packet header after header.
We peel the packet, we fill.
For example, the simulation model, we have template there, we have activator, we have.
Yeah.
So activator is going to take care of the
Yeah, right. We don't have to worry about that. Basically, what we can do is we can look at the whole thing, and then right away we know the decision. Okay? All right. Having said that, I'm going to tell you just the opposite. Actually, it is not that simple. You can't find the IP header because you remember this morning we talked about that header is inside a header inside a header, and we keep more headers. So to find where Ethernet address is, you may have to look inside somewhere. It's not always outside. So this is how it is done. First, you find out the input port which is available. You know that it came from wire number 1, interface number 1, input interface. And then you find out the Ethernet source address, destination address, and type. Set everything else 0. So this is from the outer header, right? Then if the Ethernet type is 8100, that means it is a VLAN tag, right? If there's a VLAN tag, then find out the VLAN ID, VLAN priority, and find out the ether type now. So there are two ether types. The first ether type says VLAN. Then you go inside the VLAN, there the ether type says this is an IP packet. right? So you have to find out the second VLAN, second ether type, and then you go back in this here, okay? Now, if ether type is 0806, then it is an ARP packet. All right, if it is an ARP packet, then you find out the source and IP destination, etc., inside the packet somewhere. If it is not an ARP packet, then it is 0800. Ether type is 0800. 0800 means IP. If it is an IP packet, then we see if it is a fragment. If it is a fragment, not a fragment, then you can go ahead and look up. If it is fragment, then you have to go inside and do whatever, right? Then you have to see whether it is a TCP or UDP. IP protocol type 6 is TCP, 17 is UDP. And then you find out the TCP port numbers, destination port number, etc. If it is not TCP UDP, is it ICMP? Is it ICMP? Then do whatever. So it's not just that you take the packet and you match it. You have this whole algorithm. Okay? You have to go step by step before you get to this thing where you can match. See, the table entry matching is here. Okay? So this is the part you have to know, that people think that it is just very simple, straight header match. It is not a straight header match, because to find the header, you have to go through many things. Okay? Counters. Counters could be per table, means the whole table. Per whole table, you find out how many entries are active, how many packets have been looked up, how many packets have matched. There could be per flow. What is a flow? Flow is each row. So anything that matches this is one flow. Anything that matches this is second flow. Anything that matches 3 is this flow. So every flow is one row. Right? So per flow, you could have how many packets were received, how many bytes were received, how long the flow was. So when the first packet matches that row, we note down the time, that this is when the flow started, and then nothing matches, we know this is how long the flow has been active. Right? So we know the flow duration. Duration is measured in seconds and nanoseconds. So it could be 3 seconds plus 200 nanoseconds. Per port, every interface, we measure how many packets are received, this, and so on and so forth, errors, and then per queue. Now each port, each interface has multiple queues. Remember, in the Ethernet we had 8 queues. So for each queue, you may have to count. But all of this is specified in that row entry as to which counter to increase. Actions. Now the actions could be simply the send to port 1. But oftentimes it is more than one port. So there are many virtual ports which have been defined. For example, a virtual port all means send it to everybody except the input port. Broadcast, right? I mean, something like that. Controller. Virtual port controller means send to the controller. Local means send to the local stack. Table means go to the next table. In port means send it back to the input port. Normal means use your standard Ethernet stuff, traditional Ethernet. And flood means send it along minimum spanning tree. So that is slightly different than all, because in a spanning tree, many links might be disabled. NQ means to put a particular queue, drop, or modify a field. The action could be that simply change the TTL, do something else, right? So anyway, so these are all different actions. Continuing along the action line, masking allows matching only selected fields. So now you saw most of the entries were stars. That is called masking. So we are not going to look at those fields. We're going to look at only certain fields. If header matches an entry, corresponding actions are performed. If no headers match, the packet is queued and the header is sent to the controller. So this is what happens. You go through the end table. Wherever it matches first, you're done. If it doesn't match, now you have to send it to the controller, the header, total header, and say, look, I have this packet. It doesn't match any of the entries I have. What do I do with it? You keep the packet in a queue someplace. When the answer comes back, then you send the packet off. Controller can change the forwarding rule if a client moves. So basically, modern switch is already implemented. So the thing is, so now there is a whole thing about matching the table. And for those matching, you need TCAMs. The way matching is done right now in the switches, we have to simply match the destination address. What we do in the switches is when we get the packet, we take the 48 bits of destination address and we have a TCAN. In that we match it and we send it off. Right? Now we match this thing to find out which rule to use. So the TCAMs are used for that. Controller can change the forwarding rules if the client moves, and packets for forwarding clients are forwarded. So if somebody moves, that is very easy to do right now, because the controller will know that now this host, which was in this room, is now in that room. So it will tell everybody, now change your forwarding table. So if the destination address is such, send it to room number X. Now controller can fill the entries beforehand or afterwards. So it can just tell you the whole thing beforehand. So you don't have to wait for the controller. Or it can send it when you ask for it. So both are allowed, proactive and reactive. Yeah. Right. So the question is, what if I was under controller 1 and then I moved to controller 2? What will happen? Basically, there has to be a protocol between the two controllers to say that, this guy is moving from here and then this guy moved here, from there. Right now, that protocol does not exist. So I will come to that, issue towards the end of this. Right now, there is no protocol between controller to controller, but that is what is required. If you want to continue the flow, the thing is, one thing is, if they don't know, then when you come into the new controller, it will start saying, okay, now send the packets here, but your old packets will get lost in the old area. And that's what happens on the internet today. Basically, when you send something, and if you move, your connections are all TCP connections are disconnected, and you lose the old connections, you have to restart in the new place, your FTP or whatever you are doing, right? It doesn't continue. So, but there is hope that if somehow we could tell the controller that, look, this flow was coming here, now it is going there, so this packet should not be dropped, this should be sent there. So if there was a controller to controller protocol, which is not there right now. Good question. And so anyway, so the idea is this is somewhat powerful, so everybody wanted it, and every company now makes a switch which implements OpenFlow. Arista, Brocade, Extreme, Huawei, HP, IBM, Juniper, NEC, you name it, they have it. But more than hardware switches, there are software switches. These are the switches that you can put in a hypervisor. And so Indigo, Link, so on and so forth. The most important one is Open vSwitch at the bottom. Open vSwitch was done by Martin Casado, the same guy. And so Open vSwitch is the most commonly used switch today. It is a software piece. You can download it, you can use it, you can make a switch out of a PC. And it can run inside a hypervisor, it can run by itself, it can run as a distributed switch around multiple servers, and it is a default switch in every cloud computing stack that we know of. It is in Gen Server, Gen Cloud Platform, Promax, VirtualBox, KVM, OpenStack, OpenQRM, OpenNebula, OpenWord. If you know any of these names about the cloud management systems, they all use this right now. If you are going to do any research in this area, you are better off downloading Open vSwitch, and we have done it. We do research on this area, and you can even download it on a little Raspberry Pi computer, $25 computer, and you have an OpenFlow switch. Okay? Distributed with Ubuntu, Debian, blah, blah, blah. So this is everywhere. Intel also has a version of it. So Open vSwitch is all you need to know. What does it do? It does everything that you need to do because it's open. Because it's open, its source code is available. You can modify it. You can implement whatever protocol you want, and everybody else who has modified it puts it in public domain. So you can get theirs as well. It does a NetFlow, JFlow, SFlow, NetStream, IPFix, RSPen, whatever. Everything listed on this page actually is what we call monitoring protocol. You can monitor what is going on in the network using these protocols. for example, GRE tunneled mirrors, what they do is that if the packet is going out of port 1 and you can say, well, everything that is going on port 1, please send me a copy to port 3. So you are monitoring there, right? So that is called mirrored port. So you can monitor what is going on in the network and you can take actions if something goes wrong. Then it also does link aggregation control protocol, where you can combine many Ethernet links into one link. You can do 802.1 Q VLAN, connectivity fault management, bidirectional forwarding detection, spanning tree, per VM traffic policing, OpenFlow, IPv6, whatever. I mean, so the thing is, this has been around for some time by now, and people have updated it, modified it so that it is kind of very complete switch. And to manage it, you need to implement OVSDB. OVSDB is Open vSwitch Database Management Protocol. So basically, it is managed by a database. You have a database server which is in the switch, and you have the controller which is actually a client in this case. So it can ask the server, please give me this data. Okay, please write this data, read this data, whatever, right? Commands are coming here. The server will do that, and the response will go back to this. And actually, this is the management part of the thing, right? So you can manage it using this database thing. And you just publish subscribe, right? Publish subscribe means that this is the publisher. The switch is the publisher, and you can have many managers who can basically read the data. They can be the subscriber, right? And obviously, so this is OVSDB is to manage. OpenFlow is for changing the table. If you want to change the OpenFlow table, then you will use OpenFlow. But if you want to manage the Open vSwitch, now here's the thing though, I mean, like you have to differentiate between Open vSwitch and OpenFlow. Open vSwitch is a general switch. You don't have to have OpenFlow in it, right? It could be a normal switch bought from Cisco, right? If you want to implement that. And if you want to put OpenFlow, you can put that too. So it's all basically Open vSwitch is a general switch. You can put anything inside it you want, including OpenFlow. So if you put OpenFlow, then you can speak OpenFlow. Otherwise, you will speak OVSDB to configure it. Everybody understand that part? Right? The relationship between OVS, Open vSwitch, because Open vSwitch is everywhere. Okay? That doesn't mean that these guys are using OpenFlow. Just using Open vSwitch. Because Open vSwitch is required for this morning's, I have to go back to this morning's tutorial, is that every VM needs a virtual switch inside it, right? Every machine needs a virtual switch inside. So that is Open vSwitch. All right. Now, so far what we have talked about is OpenFlow version 1.0. Every hardware switch that you will find today is OpenFlow version 1.0. But as soon as 1.0 came out, people started making the hardware and started selling it. Then they realized that there are many things they cannot do. So they have to update it. Version 1.1 came out, and they could. What is the thing they could not do? They could not do MPLS. They could not do Q-in-Q. They could not do ECMP. They could not do multicast, etc., with version 1. So 1.1 allows you to do some of these things. So first thing new here is table chaining. Instead of one table, now you have multiple tables. And the action could be simply that if you match this table entry 1, then go to table 3. If you match entry here, then you go to whatever table. So there could be pointer from one table to the next table to the next table. And also there is a special table called group table. And the group table has many entries, as we'll see in the next slide. But so the idea is now you have controller and you have the element, forwarding element, which has many tables, which are chained sequentially. And the reason you need this chaining is because in MPLS, you could have VLAN, you could have MPLS tag inside an MPLS tag, whole stack of tags. How do you handle that? You look at the top level and then you go to the next table to look at the next level and next table to go to the next level. And there are many situations where you really need to do first matching and then go finer matching and finer matching and finer matching. All right. So that is what table chaining is about. And so that allows you, table chaining allows you MPLS and MPLS traffic classes. Then next change in OpenFlow 1.1 was that on a miss, the instruction can be sent to the controller or continue processing in the next table. So what happens previously in 1.0, you go through 1 through n. If you don't match anything, just have to send it to the controller. Right? With 1.1, there is an entry at the end which tells you if you don't match anything up to now so far, then send to the controller or drop it. So now you have two choices, or it could be that go to some other table, next table. If you don't match this table, go to the next table. And the group table that we talked about, the last one, this is a special table because it has more than one actions. It has a group of actions. And you may be asked to do all the actions, such as forward to port 1, port 3, port 5, port 7, all of them. Or you could be asked to select one of them, send 1, 3, 5, or whatever. Or it could be that, it will tell you indirectly where to go and do the actions. And fast failover, that basically if see which port is active. So it will say try port 1 first. If it is not active, then go to port 2. First live port it will send. So there are many alternatives in the group table. So with this, we can support multipath, MPLS, Q-in-Q, and tunnels. Okay, OpenFlow 1.1. Now the interesting thing is that OpenFlow version 1 switches cannot do 1.1. Obviously, right? Since they cannot do 1.1, the old hardware switches are no good. If you want to go to 1.1, you are stuck with 1.0, or you really need a software switch, which can be easily be changed. Well, 1.1 was done, then we realized that there is something else missing, and that is IPv6. So IPv6 was added in 1.2, and then the matches were made little bit more more TLV type length and value. So rather than simply saying that you do the port number this, in the table, if you remember, there was a specific field. Now in the specific field, now you can have TLV. So if this is the type, sorry, 1.2. If this is the type, and this is the length, and this is the value, then do that. So now you have more general fields matching. And that also allows experimental extension. So any vendor, Cisco, Juniper, etc., can put their own fields and say, if this is the field, this is the value, then do this. Question or something? No? Okay, by the way, all of these specs are public. You can download them from the URLs which are in the bottom of the slides. Every slide has a reference, which is a good starting point. And after that, basically, you can either read that and do Googling, and you will find more. Yeah, go ahead. It don't match. See here, there is no place where you can match IPv6. So basically it will end up here. I think what will happen is you will send to the controller, maybe controller will say that, see, thing is there is no way to specify IPv6. That's the problem right now. Service MAC, so source MAC to destination MAC. Yeah. So the thing is, okay, so here's the thing. As long as you just keep your matching to the MAC level and don't specify, then it will find the right MAC. But if when you have to cross the router and go to some other IP address, then it is a problem that you will run into. You can get from here to the router, which is in the same LAN. Okay, all right. So what you are saying is, what you could do is, you could have a controller control a LAN, and you will be able to cross it regardless of what kind of traffic it is. In fact, you can do just the MAC. The router itself will send you to some other LAN, and then you can use another controller to cross that LAN. Okay.
So we can do some upload to zero, have a hardware switch, and we can compare it with IPv6.
As long as you ignore the whole IPv6 system. See, you can do 1.0 as long as you don't look at the IP addresses, just based upon source MAC, destination MAC, VLAN, ID, and priority and Ethernet type, you are okay. Because this would be star, 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 star. Right? And what will happen is, here, you see, this is the part. So what will happen is, you will come here and you'll say, is it IPv4? 800 is IPv4. And you will say, no, it is not. So then you will come back here and you will say, all right, everything is matching. Now let me see if it matches the every entry. And if it matches everything that you have found matches and everything else is don't care, it will go, right? All right. So IPv6 started in version 1.2. And experimental instructions basically are the vendor extensions. You know, the manufacturers can put their own extension. 1.3, now IPv6 was supported in 1.2, but not the extension headers. You know what is an extension header in IPv6? IPv6 has base header, and then there are lots of extension headers. Some of them are destination extension headers, some of them are per hop headers, and so on and so forth. Those were handled in 1.3. MPLS was handled in 1.1, but the bottom of the stack bit was left out. You see, MPLS has a stack of labels, and then there's a bit that says in the label, there's a bit that says bottom of the stack, means no more. That was left out. So that is here. MAC in MAC is here. Tunneled ID metadata. And so if there is a VXLAN and other things that we talked about this morning, those can be handled here. Per connection event filtering. And so it is possible that one switch may have multiple controllers. It's like this. One physical switch can become multiple logical switches, multiple virtual switches. And first virtual switch reports to controller 1, second virtual switch reports to controller 2, third virtual switch reports to controller 3. So you could have multiple controllers because you are virtual, right? And so that is better handled in this one. Many auxiliary connections to the controller allow expert parallelism. Previously, everything was going on one channel. So whenever you wanted to send something, packet number 1 didn't match, you sent to the controller. Packet number 2 didn't match, you sent to the controller. And you send packet number 3 to the controller. Now there's a big queue waiting there, and when the 3 came, it is waiting for 1 and 2 to finish before 3 can be done. Now with parallel paths, now you can have many parallel connections to the controller. You can send 1 along this, 2 along this, 3 along this. While the controller is figuring out what to do with 1, it can answer you for 3 or 2 in parallel. So now instead of one controller, one TCP connection, you have multiple TCP connections. Okay? Better capability negotiations. So now because somebody is speaking 1.1, somebody is speaking 1.0, somebody is speaking 1.2, so we have a capability negotiation feature which says that, you tell me what do you speak? You say, I speak 1.1. Okay, so here is your table. So I speak 1.2, here is your table. So that had to wait until version 1.3. More general experimental capabilities. So now here they generalize the vendor extensions even more, and table mesh actions, separate flow entry, like we talked about, what to do if you miss the table totally. Cookies were added. So cookies basically are the state, just like when in the HTTP world, we put a cookie, we send the cookie to the server. That way server can figure out who you are, what we have done so far. The whole state is in the cookie. Similarly, the cookie is sent to the controller. So when controller receives a message, it knows what context it was in. It doesn't have to keep the context. Duration field has been added to most stats. So most of the counters have duration as to how long they have not been reset. Per flow counters can be disabled, and per flow meters can be, and then there are meters and meter bands. So what is a meter? Meter is simply a rate. So you can count the number of packets and you can count the duration. If you divide, you get how many packets per second or how many bytes per second. So that is a meter. And now you can put a threshold on the meter. That is called the band. So you could say if the flow is less than 10 megabit per second, then don't do anything, then forward it. If it is more than 10 megabit per second, up to 20 megabit per second, please mark the packets with discard eligibility. After 20 megabit, throw them away. Okay, so you can have a meter, which is a rate, and you can have a rate limit, which is a band, and you can have the band action. If the flow crosses a limit, you can have the action. All right, so now we can do quality of service policing and other things that were not possible before. This is 1.3. Now 1.4 added optical ports. So optical people got interested into open flow, and optical people don't do packet switching, they do circuit switching, they do wavelength switching. So now they can use open flow. Basically, the table would say if you are coming on the red color on fiber 1, then go to the fiber 2 on a blue color. So you do wavelength switching. Okay, and so that is allowed. Again, everything was made a little bit more general. So TLV encoding is mostly done in most places. More extensions for the API, for the experimental and vendor instructions, and then more information when a packet is sent to the controller. Previously, when the header was sent, it was just the header field. Now you can send some other things, such as TTL is 0, or I got the packet, it matched the entry, but this is what happened. So whatever event happens, you can just tell them. And then the switches can evict entries of lower importance if table full. So every entry has an importance. So whenever the table is full, they look at the lowest important priority entry and throw it away rather than by time like they were doing before. So not before every entry was equal priority. Now the entries have different priorities. Switches can notify controllers if the table is getting full, and atomic execution of bundle of instruction. So what is atomic execution of bundle? First of all, bundle is, you might be asked to do 4 things. 1, 2, 3. Change TTL, change QoS, and forward. Right? That is a bundle. Now, atomic means that you do the whole bundle or you don't do any of those. So you do all 4 instructions or do 0 instructions. You don't do 2 and then halfway you're stuck. So atomic execution is added in this version. Any questions about any of this? Well, that is where we are right now. The version 1.4 is the latest version available. It started with 2.09 version 1, 2009 version 1, and October 2013 version 1.4. These are all official versions. This version 1.4 is still, even though the spec is available, but it doesn't say approved. So maybe it is still going through approval phase. There were version 1.31, 1.32, which are simple bug fixes, so I didn't talk about them. But as you can see, 1.1 added MPLS, ECMP, and QNQ. 1.2 added IPv6 and TLV. 1.3 added MAC and MAC and multiple channels. And 1.4 added optical transport networks and bundle instructions. Now, bootstrapping. Bootstrapping is how does a switch, what does the switch do when it just comes up? You turn on the power on a new switch. Well, the first of thing is that when you turn it on, you have to tell it something before it can do anything. You have to tell what is your IP address, what is your controller's IP address, and what is your default gateway. Just like when you bring up your computer in any place here, you have to put in those numbers. You have to put in what is your IP address and what is your default gateway, what is your DNS address, right? If you don't put in, the computer will go nowhere. Generally, what we do is we use DSCP. DSCP gives us the address, gives us the default gateway, gives us the everything else, right? So, but you have to do the same thing here. Except that there's no DSCP which can give you a controller's IP address, right? So you really have to have a protocol that can do that for you, and there's a protocol for that, which is equivalent to DSCP, which is coming up in the next slide. So once you get these pieces of information, then you can talk to the controller, because you have your IP address and you have the controller's IP address. Now your table is empty, so you don't know anything about how to forward anything, but you can send a message to the controller saying that, look, I'm here, new. Controller will send you one table entry, and that table entry simply says that if you ever get an LLDP packet, send it to all ports. What is an LLDP packet? An LLDP packet is the link level discovery protocol. That's an Ethernet discovery protocol where when you come up on the Ethernet switch, if you are a host, you just send an LLDP packet. It is broadcast to all the ports of the switch, so you know who your neighbors are. At the switch, when it comes up, it sends to all the hosts, so it knows who it is connected to it. So it basically, discovery means it says, hello, I am up, who are you? So you say, well, I am MAC address such and such, and I can do link level aggregation, and I can do this, and I can do 802.1 QH, whatever. So all those capability negotiations are done through LLDP. So the controller tells the switch that whenever you get an LLDP packet, forward it to all your ports. And then the controller does send an LLDP packet right after that. So when the switch gets the LLDP packet, it looks into its table. The table says send it to all the ports, it sends it to all the neighbors. And the neighbors table has already been programmed. Their table says that whenever you get a LLDP packet, send it to the controller. So all these packets go to the controller, and the controller knows who your neighbors are. Like, you don't know yet, but they know. The controller knows who your neighbors are. Then it makes a whole table for you, routing table, which says, well, this guy is connected to that. And so now, when the packet comes from A to B, it should go like that. So now I will fill in the whole table for you. Okay? Bootstrapping. Now, we said that somebody has to tell you your IP address. Well, that protocol is called configuration protocol, open flow configuration protocol. It's a separate protocol than the open flow protocol. Open flow protocol simply gives you the tables, but if you want to do any management or configuration, that is done by OF-config. That is the name of the protocol, OF-config. And OF-config can do things like IP address, port number of the controller, whether we should use TCP or TLS. TCP is the normal TCP protocol. TLS is the secure TCP protocol, right? I mean, it's like SSL we use on the web, HTTPS. So transport level security, TLS protocol. It will also tell you how many queues on each port. So remember, each interface, each wire has many queues. And so this OF-config can be used to tell that you should have 4 queues, 8 queues, 2 queues. Enable and disable receive, forward, speed, media, etc. It will tell, well, on port 1, you should send only a 10 megabit. On this, you should send a 100 megabit, things like that. And you should disable this port or whatever. So anyway, so the initial configuration is done by OpenConfig, OF-config. OF-config also has multiple versions. So when 1.0 OpenFlow was done, there was OpenConfig version 1.0. When 1.1 was done, then we needed different configuration. So there is another version of configuration 1.1. although they do not correspond. So 1.4 config will not correspond to 1.4 OpenFlow, but every time a new OpenFlow version comes up, a new version of OpenConfig has come up, and maybe intermediate as well. So they are not same number. Now, OpenConfig is actually a little bit more general. It allows you to do this virtualization. So one physical switch could be made into many logical switches, many virtual switches, where this logical switch consists of 2 ports here, this logical switch consists of these 2 ports there, and so on and so forth. So you can take one 48-port switch and make many logical switches. And each logical switch could be controlled by a different controller. All that information is coming from OFConfig. OFConfig protocol can tell you that, okay, port 1 to 15 are first switch, and they report to this controller. Your port 16 to 32 are this switch, the second switch, and you report to that controller. So concepts, actually, I think we have talked about everything here. You have one capable switch, which is a physical switch. Configuration point is, this is the configuration point. This the thing that speaks the OFConfig is called configuration point. So this is configuration point. Now, by the way, you should remember that this is a function, and packaging can vary. So this is a function. It could be in the same computer that has the OpenFlow controller. So it's not that you need a different box. It's just a different function. Okay? And then controller is there, operational context, basically which logical switch we are talking about, how many queues, how many ports, how many other resources such as certificates, tables, etc., etc. And the data path ID. Each switch has an ID. 64-bit ID, of which 48 bits are the MAC address of some particular port, and 16 bits are we just assigned, so that we call this switch as some number followed by the MAC address of first port. Okay. Anyway, OFConfig. Oh, yeah, here are the versions actually. So I was thinking I didn't have a slide on versions. Version 1.0 based upon OpenFlow 1.2, 1.1 based upon 1.3, 1.11 bug fix, 1.2 based upon 1.4. So actually it looks like they are corresponding except followed by 0.2. So 1.2 is 1.0, 1.3, 1.1, 1.4, 1.2. So you just subtract 0.2 and you get that. So basically, so the idea is that every time a new version of OpenFlow comes up, there is a new version of OpenConfig. And here are some of the new features that we have not talked about. Configuration of certificates. So because everything is encrypted, all the communication in OpenFlow has to be encrypted, you need certificates to be able to negotiate the keys. Capability discovery and then VXLAN, etc., topology detection, and assigning resources to logical switches. So this is where virtualization started happening. So anyway, so these are different. So if you go to website Open Networking Forum, you will find 4 versions of OpenFlow and at least 3 versions of OFConfig. Then there is another protocol called OpenFlow Notification Framework. So notification is something that is an event that basically happened, and you have to inform your manager. So, for example, if a link goes down, you have to inform your manager. Previously, this was just done as with the controller, but then later on they realized that really this is a totally separate function, nothing to do with the table, etc. And so we should have a separate framework for it. So now there is an OpenFlow notification framework, and it uses publish subscribe model. So each switch is the publisher, and you could have as many subscribers as you want. You could have many controllers that could subscribe to this switch. Whenever something happens to that switch, some event happens, it looks at the list as to who is subscribing to this, and it tells those guys, look, this link is down. So this could be more than one subscriber. It doesn't have to be one controller. Okay, this is a management function, more of a management function than control plane. So the management happens in the notification framework. ITU already has a very good notification standard, so they have at least the terminology well defined. That terminology is used, and then previous version of OpenFlow already had some notifications which were part of OpenFlow. Now they are being moved into this framework. So then the OpenFlow remains mainly control part, management comes out. So the pre-existing notifications such as packet in, flow removed, port status, error, hello, are the configurations such as new logical switch, capability change, and all of those things. These were previously part of the OpenFlow. Now they are part of the OpenFlow notification. And you can tell to any of the subscribers. So much about OpenFlow and the protocols. Now the critique of it. So some people are complaining that it is not easy to implement because there are so much matching to be done. Right? You may have to match so many fields, and there is a whole new industry on searching because matching is searching, basically, and so there is a whole new set of people who are designing keycams that can match that many fields that fast. Multiple tables, each with a large number of flow entries, instructions and actions for each table, and VXLAN and MVGRE are partly supported. And for a very large network, the number of flows can be very large. The number of entries can be very large. And so that is a critique. So what is OpenFlow? Next question item. First, basically we need a northbound API. What is a northbound API? Northbound is that the OpenFlow controller tells the switch whatever it needs to do. But how do we tell the controller? So somebody has to tell the controller that I want all traffic going from 191, 192 to be dropped. Right? So you have to tell to the controller. Right now, every controller program has its own way of finding that out, being told. So the API is not standard. So basically, the northbound means this is not standard. Southbound is standard. Southbound is standard. Right? Southbound is OpenFlow, but northbound is not standard. Then controller to controller is not standard. So if a controller wants to talk to another controller, that is called east-west, that is not standard. So if you want to go to other controller, east-west is not standard yet. There is no standard for east-west API. And what you do with the controller is down. That is not standard yet. And there are many things which are not still supported. Although they reached up to IPv6 and extension headers, but there are many things that are still, you cannot do. And it handles the flows very good. See, the flows are good because if you match the first packet, all other packets will match that entry, and so they will go fast. But these are called elephants. So it is good for the elephant. There is other kind of traffic called mice. Mice means just you request something and you get a response and you're done, like DNS request. If you have a request response type, then every time the request comes in, you miss the table, and then you have to wait for the whole thing, get the answer, send the entry through, and then it will not be used. Right? So it's not very good for mice. Need API to encrypt data plane packets. Now, there are some places where you need to encrypt the packets. For example, if you have a router going from out of your company to another branch of your company, you want to put that VPN. You need to encrypt the packets at this end and decrypt at the other end. So you need an action item which says action, encrypt the packet with this key. That doesn't exist yet. So firewall, IDS, etc. cannot be done. Need to program an abstract view so that source to destination without knowing the physical network. So the whole idea of all this is to have an abstract view so that you can go from anywhere to anywhere. But because the northbound API is not there, right now it is not easy. But once the northbound API comes out, maybe, this will become easier where you don't really need to know about the network anything, and the controller can figure out the whole tables. Any question about anything so far in the OpenFlow? Is it all going through? Huh? All right, OpenFlow, there are many controllers: Knox, Spark, Snag, Beacon, Trema, Maestro, Floodlight, Onyx. But you don't have to worry about any of them. The last one is the most important, that is ONOS. ONOS is the latest controller from Stanford University. ONOS means Open Networking Operating System. And it is a distributed OpenFlow OS for the WAN. So basically, you can have many controllers. Now they can talk to each other somewhat using this database stuff, big data stuff. So they use a distributed registry which uses Zookeeper. So those of you who know big data know that along with Hadoop and other things, there is a Zookeeper which allows you to do distributed registry. Similarly, there is something called Cassandra in big data field. The Cassandra allows you to do DHT, distributed hash table, and so on. So those things basically are part of ONOS. You can have 8 to 10 controllers in a cluster. So these are multiple controllers which are in a cluster, and then they talk to the forwarding element, and they somehow synchronize using these features that we talked about with big data. And so if one controller goes down, the others can take over. Okay. So now, basically they have introduced this reliability using the distributed database concepts. Then there is a module from Stanford, also called OVX, Open Vertex, which sits right here under the controllers. And this allows switches to be virtualized and each virtual switch to report to a different controller. So what happens is, if this switch is connected to this controller and this switch is connected to this controller, whenever the message comes in, the Open Vertex knows which virtual switch is connected to which controller and sends it to the right controller. Similarly, when the message comes from the controller, it knows which switch it is intended for, and it sends it to that way. So it basically allows you to have multiple controllers for multiple switches. Okay? So this is a virtualization platform, and allows you to virtualize the data center. So everything that we talked about in the morning, actually, this is very powerful. Everything we talked about in the morning, having multiple L2 networks, multiple L3 networks, you can do that using this OVX. One more piece of software that is very useful is Mininet. So Mininet is a emulation environment. Using Mininet, you can emulate any network with whatever software you need. Some of you are used to NS2 for simulation or OpNet for simulation. This is emulation. So you can have with Mininet, you could have some real routers and you could have some virtual routers. You could have some software routers. So Mininet actually allows you to set up a configuration such that you could say, well, I want 5 nodes on the network. Third one is a bridge, and that bridge is following, this OpenFlow, whatever. And so it is not related to OpenFlow. What it is this is very general. Mininet is very general, and you can use any module, any protocol. Most of these modules are available, including OpenFlow module. So you can install OpenFlow wherever you want. Okay, and you can play with that. And this is how we do our research right now. We can't afford real hardware, any hardware switches anyway. So what we do is we have a mini net. In the mini net, which runs on our laptops, we can simulate small networks and we can see the actions. Okay, if you want to do small cloud computing research, cloud computing emulation, you can do that with Mininet. It's a very powerful program, so try to play with it and see how it goes. Okay. That brings us to the end of first part. The summary of this part is there are 4 planes of networking: data, control, management, and service. The open flow separates the control plane and moves it to a central controller, and the rest is called forwarding element. The switches match the incoming packets with the flow entries in the table, and the controller supplies the flow tables and other instructions. Right, so basically the table comes from the controller, and the switches just use that table. And then OpenFlow has been extended in version 1.1, 1.2, 1.3, 1.4, etc. to IPv4, MPLS, IPv6 optical network, but there is more to be done. Then in terms of software, we have ONOS controller, we have OVX for virtualization, and we have Mininet for emulation.